It's been 5 weeks, and we're down to the last few rations. But our probes finally might have found the second solution. We already have one solution, which is true for y1 in this equation right here. This is just a regular old second order differential equation, homogeneous equal to 0. But we can use the reduction of order technique to create a first order linear differential equation. We'll start by assuming that y2 is going to be equal to some sort of u of x times y1. That means that these two solutions, y1 and y2, are linear independent y's. Now as we start taking derivatives of this y2, since both of these are a function of x, we have to use the product rule when we do that. Well, essentially we'll take the first derivative and plug it back into here, and take the second derivative and plug it back into here, and then we're going to end up simplifying this into a smaller equation that will be something like y1 times, well, I'm going to introduce a dw here. We'll explain what that is in just a moment, but dw over dx, and then we can go ahead and do plus, this is going to be 2 times the derivative of y1, dy1, over dx, and we have plus p of x, y1, and then we have a w over here in the end, and this is equal to 0. This is the first order linear equation that we get when we plug in the derivatives of y2 into this equation. We simplify it into this. Now where did the u's go? Because suddenly we have these w's that just appeared out of nowhere. Well, what I was doing sort of as part of all that algebra is that there was this dw, this portion when we did a little substitution. We took dw over dx, which is simply equal to the second derivative of the u, so dx squared here. So at some point along this process, we switched these u's into w's, and it turns out that dw is the second derivative of the u, and that means that if we were to integrate that, we get that w is simply going to be equal to du over dx. So we have sort of the first derivative, then the second derivative. We just substituted those into w's. This might be getting a little crazy, but the idea is that you're going to integrate the w, and that's going to lead you into the u of x, so that way you'll be able to plug that into here, and you'll be able to get the second solution, so that you'll have a final answer of y is going to be equal to, it's a constant times the first answer, call that c1 y1, and then we have a constant times the second answer, which is y2, c2 y2. But there's another way to get this second solution. We can also use the integral y2 is equal to, we'll start with y1, and then we'll integrate e to the negative p of x dx is going to be divided by y1 squared, and then this is over dx. Now it's important to note that these guys right here, these don't cancel. You might notice that at some point along this integration, you'll end up with e to the power of c up here. And just realize that e to the power of c is the same thing as just a regular constant. So you can pull that out of the integration, and so all constants that are inside of this integral can actually get added into the c2 constant over here. They get absorbed into c2. So you don't even have to include them into this integral, which makes it nice.
Excuse me. So like when you say two solutions, what are you talking about?
Well, an invisible force field pulled the M30 spaceship into this desolate planet, and it's an absolute nuclear wasteland of sulfuric vapors and toxic streams. And we still haven't found any sign of alien life. And the only way we've been able to survive here was by solving these second order differential equations. Let's begin when the second order equals some f of x, where the f of x is going to be either exponential, e to the x, a sine, a cosine, or some kind of polynomial. It can only be one of those four. Here's a simple equation. We'll say that d squared y over dx squared plus dy over dx minus 2y equals 3x. Usually we're looking for a general solution, which is in the form y equals y homogeneous plus y particular. The homogeneous solution simply equals 0, whereas the particular solution is going to be equal to the f of x. So when we have a homogeneous answer, the yh, that's going to be equal to c1 y1 plus c2 y2. And that's exactly what we got over here. This answer was actually a homogeneous solution. We want to solve for the homogeneous solution here. We're going to use an auxiliary quadratic equation that we can derive from the second order differential here. Let's imagine that these differentials were just a variable m. So we could say m squared plus m minus 2, and we'll set that equal to 0. So that way we'll solve for when the case is equal to 0. We'll find the roots of this quadratic equation, and notice we're just using the coefficients here that are in front of that function. We'll solve for the roots of this quadratic equation, so we'll get something like m plus 2 and m minus 1, and that's going to be equal to 0. So that gives us an m1 being equal to 1 and an m2 being equal to negative 2. So we should be able to get the answers y1 and y2 from those m's. We'll say that it's equal to e to the power of m1x or e to the power of m2x. Substituting that back into this equation, we'll find that the solution here is going to be yh is equal to c1 times e to the, well, we just have 1 for m1, so we'll just say it's e to the power of x. And then for the second one, we say plus c2, and then this is the second solution, so we'll say e, and there's a negative 2 there, so we'll just say negative 2x. That would be the solution to the homogeneous portion of this answer. Now let's just keep in mind that quadratic equations have a lot of different types of answers, and sometimes you'll get the same solution, like m1 equals 1, m2 equals 1, m3 equals 1. Well, what are you supposed to do there? If you have y1, y2, and y3, what you would do is you'd get e to the power of x here, right? Here you'd think you'd get e to the power of x, and here you'd think you'd get e to the power of x. But we can't have the same repeated answers. So instead, what we have to do is, remember back over here, we have this type of thing going on. Well, if you tried to plug if you try to use the first answer, and you try to solve for the second one, it turns out that you're going to end up with an extra x here. So you could see you'd end up with an extra x there. And here you'd end up with an extra x squared. So if you have repeated solutions, you just have to keep multiplying by x, or you could try to plug it into this whole formula and do it that way, but you'll just get the same answer. Now, if we have a particular solution, we got to use a method of undetermined coefficients to try to figure out the answer. So let's try to set up yp, but there's going to be lots of different types of solutions. You could get the exponent, the sine, cosine, or the polynomial. Well, in the case of e to the power of something like kx, that would be an a. If you're looking for yp, it would equal a e to the kx. If you're doing a solution involving sine or the cosine of kx, then that would become, the coefficients you're going to want to look for are going to be a times the sine of kx in here. But then you also have to include b with the cosine of kx. And the reason is because when you take derivatives of sine, it turns into cosine. You take derivatives of cosine, it turns into sine. If you take derivatives of e to the power of x, it's always e to the power of x. You don't have to do any kind of changing over there. But then if we have the polynomial function like kx squared or something like that, then we have to use the coefficients of ax squared, right? Start with ax squared. And then you have to add in bx. And then we have to add in c. So that way we're accounting for all the possible coefficients that could be involved with this particular solution. Now the goal here is that, well, the k is going to be given in this answer. So we know that the k is supposed to be 3 here, right? The idea is that you're going to be looking for, you have to find A, B, and C. The way that we're going to do that is we're going to take our particular y, whichever one that we've decided upon, and then we're going to have to take derivatives of that. So we take the second derivative, and then we would have the first derivative, and then you put in the regular solution there, and then you'd set that all equal to whatever was given over here, your f of x. For our situation, let's just realize that our particular solution, yp, is going to be equal to, well, you're going to use a times x, and then we're going to throw in plus b, just some regular constant. Now we have to take the derivative of that, and then we have to take the second derivative, and then we have to plug it into this equation. The second square, the squared there, plus that one, and then minus 2 times that one. And that's all going to simplify down into this type of equation, minus 2ax plus a minus 2b. And that's going to be, we're going to set that, essentially what we'll have over here, we're going to set that equal to the 3x. So it's going to equal 3x. Let's just realize it also equals 3x plus 0. I'm going to add in a plus 0 here, because then we can kind of see how, wait a minute, this thing here has the x with it. So those two are going to match. And then this guy here matches with that one. So this equals 0, this equals that. And essentially we get the idea that a is going to be equal to negative 3 over 2 from this situation. Negative 2ax equals 3x gives us a equals negative 3 over 2. And then from a minus 2b equals 0, we get that b is going to be equal to negative 3 over 4. So now, those are the answers we plug into the particular solution, so that in the end, we get this final answer, that y is going to be equal to homogeneous plus the particular. So we'll start with the homogeneous. It's going to be c1e to the power of x plus c2e to the negative 2x. And then we have to add in the particular solution. So we'll just put a little parentheses on that one. And then here is, this is all the homogeneous version. And then the particular will go over here, so that we get this type of thing. It would be negative 3 over 2 times the x. And then we have plus, well, actually minus 3 over 4. And that should be that. Just a little side note here, just in case we have an f1 of x plus an f2 of x, like a combination function here on the right, just add them together like that and set up your y particular, the yp, set it up as like yp1 plus yp2. So now when you go and use your y particular over here, it's just going to be like a lot more complicated, but you'll be able to get the same answers. One last note, let's say we had some solution f of x is going to be equal to x, and we have a homogeneous solution, maybe it's like a c1 y1 plus a c2 y2, and then we have some c3 over here. Well then, if you're trying to set up your particular solution, let's realize usually you'd start with your highest degree. So if it was an x squared, then you go x squared, x, and then the constant. So in this case, you'd be doing something like, you'd start with just the x, and then you go into the constant. The problem is, the constant is both in the particular solution and the homogeneous solution, and we can't have repeated solutions here. So in this case, what you're going to do is you have to multiply this stuff by x. You have to multiply this by x, and since you did it here, you also have to do it here. So now you actually have to raise the particular solution by 1 degree, simply because you have the same answer between the homogeneous and the particular. So this is another sort of side note to keep in mind over here.
Come on up. We have run out of food.
Copy. Don't let anybody know. We can't have a panic right now.
I can develop some recipes for various digestible mixtures using rainwater and sawdust.
Yeah. Just be sure to add them to the lecture notes. Thank you, Atlas. Wait a minute. Rainwater and sawdust? Atlas!
Excuse me, Professor. What if it's not exponent, sine, cosine, or polynomial?
Good question. If that is the case, we must use the variation of parameters with the Wronskian to find the solutions. Let's start by differentiating y equals u1 y1 plus u2 y2. Keeping in mind these are all functions of x, so we have to use the product rule a couple of times. If we do that and plug it back into our original second order differential, we get a system of equations out of it every single time. It always looks like this: y1 du1 over dx plus y2 du2 over dx equals 0. And then we also get dy1 over dx du1 over dx plus dy2 over dx du2 over dx equals f of x. So this is what we get when we use the variation of parameters technique. We get this system of equations. Now, from linear algebra, there was this thing called Cramer's rule, where we could solve for du1 over dx and du2 over dx, pretending that they were like the x's and y's in a system of linear equations. So you'd have that du1 over dx is going to be equal to what we're going to call the Wronskian is going to be the coefficients here, w, and then you're going to subtract or divide that by w1, which is when you plug in the answers to that column. So we'll see how that works in just a second. And then du2 over dx is going to be equal to w over w2, where you plug the answers into the second column. So let's see what that would look like. You have the Wronskian itself, which would just be the coefficients that you find in front of these variables. So you do w is going to be equal to y1, and then over here you get the derivative of it. And then here you'd have y2, and then the derivative of it. And this is just the coefficients again, 1, 2, 3, 4. If you want to do w1, then you take your answers here and you plug it into the first column. So you say, instead of y1, the derivative of y, you get 0, and then you put then the f of x here. But everything on the right side stays the same, so y2 dy2 over dx. And then that is going to be essentially a determinant here. So you have to solve these determinants. And then w2 is going to be a different one over here. This is going to be plugging in the answers to the second column. So here we keep the first column the same, y1 dy1 over dx. And then the second column, you plug in your 0 and your f of x. And then this is again going to be a determinant. These are 3 determinants that you plug in over here. Of course, that's just going to be a function, but that'll be able to solve for this particular stuff here, because you can integrate these answers. You can integrate this, and that will take you to find u1 and u2. So once you've integrated all that stuff, plug it into the original equation, you can find your answers.
Aaron, there was an x in front of it.
No, I'm telling you, it wasn't an x, it was an x squared.
The last time we tried it with the x, it didn't work.
Yes, but it was x to the power of m.
Right, but I thought that we had to use ln of x.
ln of x was the power of ln of x.
It seems our scientists finally came to an agreement on how to solve these types of equations. They were claiming that there was some sort of an x squared in front of their derivatives here, and an x in front of the other derivative, and some sort of a constant over here, set that equal to 0. Their idea was that they wanted to have a solution in the form of y equals x to the power of m. Apparently we had to use a modified auxiliary equation, so this one turns out to be something more like a m squared plus we have a b minus a m plus c, that's equal to 0. If we look at these coefficients here, we see that a would be equal to 1, b would be equal to 1, and c would be equal to -4. That's what we'll be plugging into this equation here to be able to solve for m. But let's just imagine if there were repeated cases. It's like over here, it'd be a little bit different though in this case. Instead, we get a y1 equals x to the power of m, that's fine. But if we try to use this equation to get the next answer, y2, it would actually be x to the power of m times ln of x. If we end up getting imaginary roots, then we get this type of situation where we have a y1 and a y2. They'd be equal to x to the power of I, or maybe x to the power of negative I. If we have this situation, we have to rewrite this a little bit to get our correct answer. We'll say e to the power of ln x to the I. Then we could take I and put it in front of the exponent here. So I to the power of ln x, this is what that would be. We know from Euler's equation that if we have an answer in this form, it would simply be cosine of ln x plus I sine of ln x. And that is what this is. So you essentially get this stuff. And remember that our answer is really supposed to be that y equals c1 y1 plus c2 y2. So if we put coefficients in front of these cosines and sines, then we can absorb the imaginary component into this, and we'll essentially backtrack our way into discovering that the answers of y1 and y2 were really supposed to be cosine of ln of x and then sine of ln of x.
Okay. What did the probe bring back? Did we find a second solution? Oh my galaxies. That's not possible. How can this be? We must gather a search party at once.